So I'm going to prove to you the uniqueness of solutions with Dirichlet boundary conditions. Dirichlet boundary conditions say that, and now my t's became y's for some reason, but same function. This is 1D Laplace, and I'm going to prove that the solutions of this equations are unique. So we're going to use Green's first identity. Suppose I have two solutions to the above equation. The idea is to show that v minus w is equal to 0, because then they're unique because they're equal to each other. So let r be v minus w. Then the red didn't show up very nicely, but rxx is vxx minus wxx, and ryy is v double y minus wyy. And if you add those up, you get 0. So r satisfies the Laplace's equation as it should by principle of superposition. So what about on the boundary? Well, on the boundary, it's equal to 0. So r is equal to 0 on the boundary. Well, I'm almost done because I have a new PDE with boundary conditions r equals 0 on the boundary. Apply Green's identity with r. And we did this before. So this is Green's identity. I'm going to set k equal to r equal to h. So I wrote down Green's identity here. And I'm going to substitute in r for both k and h. When I do that, I get this equation, the blue equation here. Well, that's 0 because r is 0 on the boundary. That's 0 because Laplace r is 0 inside omega. So I'm really just left with the gradient r dot the gradient r. But that's just the gradient r magnitude squared. When you dot product the same thing with itself, you get the magnitude squared. But the only way a non-negative thing is equal to 0 in an integral, so the only way an area of a positive function is equal to 0 is if the function is equal to 0. And by properties of norms, the only way that this guy is equal to 0 is that's a property of magnitude, right? That the inside is equal to 0. So we have from there that r is equal to 0. The rx is equal to ry is equal to 0, and then you get r is a constant. By the maximum principle, though, if it's a constant, it has to be attained on its boundary, so r is identically 0. So we have a take-home test coming up next week. So on that take-home test, your guys' take-home test is going to have the wave heat, right? And your guys is going to have the wave equation. We're going to find two problems where you actually can crank out the solution. And then I'd like you to do problem 3.8 on page 26 of Sham's outline. He's already got it all in there. Just fill in the gaps, the details for your take-home test. And I did look through the solution this time to see what kind of detail he has. It's one of those maximum principle applications.